Hello everyone, welcome to today's tutorial session. Uh, let's see the first question, which is about the closures of turning decidable languages. You need to prove that turning decidable languages are closed under intersection. That is, if languages A1 and A2 are turning decidable, prove that A1 intersect A2 is also uh, turning decidable. The hint is to utilize the turning machines that decide A1 and A2 to construct a turning machine that decides A1 intersect A2. I will give you 10 minutes for proving it. Hello everyone. Let's see the proof process. Uh, First, let M1 and M2 be the tuning machines that decide A1 and A2 respectively, and construct a tuning machine M that for input W. Uh, the first step is to run uh, M1 on W, and if M1 rejects, hold and output reject. Then run M2 on W. If M2 rejects, hold and output reject. And then hold and output accept. Uh, so M is the tuning machine that decides uh, language A1 intersect A2. Hence, A1 intersect A2 is tuning decidable. Any questions? Okay, if no, let's move to the second question. Uh, you need to prove that tuning recognizable languages are closed under clean star. That is, if language A is tuning recognizable, prove that uh, A star is also tuning recognizable. I'll give you 10 minutes for proving it. Hello everyone, let's see the proof process. First, let M1 be the Turing machine that recognizes language A and construct Turing machine M that for the input W. There exists to the power of the length of W minus 1 ways to divide W into substrings. And we first list all the all these ways, and then for I equal to 1, 2, and so on. For each way to divide W, run M1 on all the substrings of for I steps until M1 halts. If M1 accepts all the substrings, then accept. And M is the Turing machine that recognizes A star, hence A star is Turing recognizable. Any questions? Okay. If not, let's move to the next question. There are three sub-questions. The first one is what is the difference between NP complete and NP hard? And the second is you run a probabilistic Turing machine on a BPP problem and it returns reject. What does this tell you? And the last sub question is you run the PDM again the same as before and it returns accept. What does this tell you? I'll give you 10 minutes for solving them. Hello everyone, let's see the solutions. For the first question, what is the difference between NP complete and NP hard? The NP complete class was defined as the set of problems that are in NP, and every problem in NP is polynomial time reducible to the problems in this class. And a problem is NP hard if all problems in NP are polynomial time reducible to it. Hence, NP hard class contains the NP complete class, and it includes the problems that are not in NP, as illustrated in this figure. For the second question, you run a probabilistic tuning machine on a BPP problem and it returns reject. What does this tell you? There is at least 2 to 3 chance that the problem rejects that input, and at most 1 to 3 chance that the problem accepts it. And for the last question, you run the PTM again, the same as before, and it returns accept. What does this tell you? This tells us that either the reject was a mistake or the accept was a mistake, and neither mistake is more likely than the other. So there is a 50% likelihood that the problem accepts or rejects the input. Any questions? Okay, if no, let's move to the if no, let's move to the next question.
Why is it 50% if you just said like the odds were 1/3 and 2/3?
Can you repeat your question?
You said there's a 2/3 chance that it rejects and 1/3 that it accepts at most. So then why is there 50% likelihood that the problem is accepted or rejected?
I'm sorry that I cannot understand your question very well.
Well, in C, you said there's a 50% likelihood that the problem is accepted or rejected.
Yes, for the question C, because we run the PTM twice, and we got different results. So we know that either the first result was a mistake or the second was a mistake, and we don't know which is a mistake, and we also and we know that neither mistake is more likely than the other, because we already know that there exists one mistake. So this is a 50% likelihood that the problem accepts or rejects the input. And for the question B, for the PTM, the probability of the PTM to generate a wrong result is at most 1 to 3. So when we get a reject, there is the probability that this problem rejects that input is 2 to 3, and the the probability that this problem accepts it is 1, 2, 3. Any other questions? Okay. If no, let's move to the next question. About complexity classes, you need to determine which complexity classes of PNP, NP complete, NP hard, BPP, and DQP the following problems belongs to. And please note that the class P is in the class BQP. There are 3 sub-questions. I'll give you 10 minutes for solving them. Hello everyone, let's see the solutions. For the first question, uh, for an input of three numbers a, b, and c, whether c equals to a to the power of b. Uh, this question is very simple, and we can utilize deterministic Turing machine to for solving it in polynomial time. So it is in the P class, and because P is in NP, BPP, and BQP, so this problem is also in the classes NP, BPP, and BQP. And for the second question, for an input of a chess game state and a prospective move, whether the move is the optimal move for that player. This problem is very hard because to determine whether the move is the optimal move, uh, this is not only related to the current state, but also related to the subsequent actions and subsequent states. And we need to compare all of them for solving this problem. And even by utilizing a non-deterministic Turing machine, we cannot solve this problem in polynomial time. So this problem is NP hard. And for the last question, for an input of an unsolved game of Sudoku, solving it. For the game of Sudoku is about a matrix. So we can utilize a deterministic Turing machine to solve it in exponential time by trying all the numbers in every position. Or we can utilize a non-deterministic Turing machine to solve it in polynomial time. So this problem is this problem is in class NP, and it is also in class NP complete and NP hard. Any questions? Okay, if no, let's move to the next question. It's about the Boolean satisfiability, and you need to determine whether or not the following equation is satisfiable. If it is, determine the values that satisfy it. I'll give you 5 minutes for solving it. hello everyone. Let's see the solution. For this equation is the intersection of four atoms. Let's first focus on the last atom. It only contains a single x4, and for the equation to be satisfied, x4 needs to be true, and because x4 is true, let's move to the first atom. This is false, and so x1 needs to be true. And for the second atom, because x4 is already true, so x2 could be either true or false. And for the third atom, because x1 is true, so this is false. So this term needs to be true, and so we can know that x3 needs to be false. Any questions? Okay. If not, let's move to the next part. This part is about prove NP hardness or NP completeness. The method is to reduce a problem A, which has already been proven to be NP complete, to the target problem B. Here, reduction from A to B means that convert the input of problem A to the input of problem B in polynomial time, and the result of problem B can be converted to the result of problem A in polynomial time as well. In other words, we can solve problem A by solving problem B. If A can be reduced to B, we know that problem B is as hard as or harder than problem A. Hence, to prove B is NP hard, we only need to reduce A to B in polynomial time. However, if we need to prove B is NP complete, we not only need to reduce A to B in polynomial time, but also need to prove that B is in the class NP. Then let's see the last question. Prove NP completeness. Assume that the undirected Hamiltonian cycle problem is NP complete. You need to prove that the traveling salesman problem is also NP complete. For a given graph G, the undirected Hamiltonian cycle problem is to find whether G contains a Hamiltonian cycle, that is a cycle that passes through all the vertices of the graph exactly once. And for a given weighted graph with non-negative weight and an integer k, the traveling salesman problem is to find whether this graph contains a simple cycle of cost which is equal to or less than k that passes through all the vertices. The cost of a cycle is the sum of width of all the edges in this cycle. I'll give you 10 minutes for proving it. Hello everyone, let's see the proof process. Firstly, to prove that this problem is NP complete, we need to prove that this problem is in the class NP. And firstly, a solution to the traveling salesman problem can be verified in polynomial time by tracing the proposed sequence around the graph and observing at the end whether the sum cost is within the budget. So the traveling salesman problem is in the class NP. Secondly, we need to reduce the Hamiltonian, we need to reduce the undirected Hamiltonian cycle problem to the traveling salesman problem, and we can map the input graph of the undirected Hamiltonian problem to the input graph of the traveling salesman problem. Then we add a weight of 1 to all the edges in that graph. Next, we add an edge if to the nodes if there doesn't exist an edge between the two nodes, and add a weight of 2 to that edge. Next, for the budget of the traveling salesman problem, we set it to be equal to n, which is the total number of the nodes. Then we run the traveling salesman problem on the graph and the budget. If the result is yes, then the result of the undirected Hamiltonian cycle problem is yes. If the result is no, the result of the undirected Hamiltonian cycle problem is no. And for the proof, you need to explain why the reduction works. Because all the weights of the edges in the graph are either 1 or 2. The cost of a cycle that passes through all the nodes must be equal to or greater than n. If the result is yes, then the cost of the cycle is equal to n, which means that all the edges in the cycle exist in the original graph of the undirected Hamiltonian cycle problem. Hence, there exists a Hamiltonian cycle in that graph. Therefore, the result of the undirected Hamiltonian cycle problem is yes. And if the result is no, then there doesn't exist a cycle that passes through all the nodes with cost n. This means that for any Hamiltonian cycle in the graph of the traveling salesman problem, it contains at least one edge which doesn't exist in the original graph of the undirected Hamiltonian cycle problem. Hence, there doesn't exist a Hamiltonian cycle in the graph of the undirected Hamiltonian cycle problem. So the result of that problem is no. Then we have reduced the undirected Hamiltonian cycle problem to the traveling salesman problem in polynomial time. And we have also proven that the traveling salesman problem is in class NP. So combine this together, we have proved that the traveling salesman problem is NP complete. Any questions? Okay. If no, that's all of today's tutorial. That's all. Thank you.